All right. Okay. So
Thank you. Start.
the title of this my talk is analysis of weak associative or weak associativity in some hyper algebraic structures that represent dismutation reactions. It's a joint work with Ilori and Oyebola. This is the outline of the presentation. Give an introduction, the short one, the background of the study. We'll look at some algebraic structures in dismutation reactions. We take a literature review. We look at the problem at hand, and I'll present the results. Hyper-algebraic structures were introduced by Marty in 1934, and hypergroups axiom. Normally, we know that in groups, in classical group, the composition of two elements is just a single element. But in the case of a hyperalgebraic structure, the composition of two elements is a non-empty set. And the motivation the motivating example is actually when you consider a group and a subgroup of each. If you consider the quotient set, then you can define an appropriate composition on that particular quotient set to have an hypergroup. Hyper-algebraic structures, they are generalization of classical algebraic structures, and they have diverse application, rough set theory, cryptography, and even in physical sciences, chemistry, physics, and so on. Given a non-empty set H with a composition, an hyper operation, we call that pair an hypergroupoid. And if an hypergroupoid has the associative property and a reproduction axiom, it is called an hypergroup. We have some other hyperalgebraic structures. They are all displayed in that particular diagram. You have hypersemi group. So an hypergroupoid that is associative is an hypersemi group. An hypergroupoid that has the reproduction axiom is an hyperquasi group. And an hyperquasi group that has identity property is an hyperloop. An hyperloop with associative property is an hypergroup. Here is the motivating example for an hypergroup based on the given hyper operation. Several kinds of hypergroups have been studied, regular hypergroup, and so on and so forth. Budzowski in 1990 introduced generalization of hyper-algebraic structure, and this has also been studied by some other authors like Corsini, Davas, and others. Such a generalization is called HV algebraic structures. For instance, an HV semigroup is a non-empty set with an hyperoperation on it, which obeys what we call the WASP property. If you take a look at the WASP property, it is the intersection of the right-hand side and the left-hand side of the associative identity not being equal to the empty set. So if a hypergroupoid is associative, definitely it has WASP, but an hypergroupoid can have WASP but not be associative. And this is a diagram depicting the interrelationship among the generalized hyperalgebraic structures, HV group, HV semigroup, HV quasi group, HV groupoid. We introduced a new hyper algebraic structure in order to mimic, to generalize a polygroup, giving a polygroupoid, giving an hyper operation on a non-empty set H with two hyper operations and a unary operation. So you call such pair a polygroupoid. So if it possesses the listed axioms 1, 2, 3, 4, then it becomes what we call a polyloop. And here is a diagram that represents such hyper-algebraic structure. So a polygroupoid that has only Roman figure 4 is a polyquasi group, and so on and so forth. Here is an example of a polygroup. Now here are some examples of non-associative polystructures. They are also hyper-algebraic structure. This very table, table 1, represents it's a polygroupoid, but however, it is neither a polyquasi group nor a polyloop. This second table represents, for an underlining set ABC, it represents a polyquasi group that is not a polyloop. And all right, my apologies for that break.
Never mind.
So I stopped at the example of the non-associative hyper-algebraic structures, polyloop, polyquasi group. So there are some physical, some chemical systems that are represented as hyper-algebraic structures. Some of them are displayed in the following tables. This is the dismutation reaction for tin. Also, you have the one for idiom. This is the one for vanadium. So we have the history of hyper-algebraic structures. Sorry, I won't be able to take us through this because of time. But the motivation behind this work is the weak hyper-algebraic is actually the worst condition. And our motivation is based on some dismutation reactions identified by Davas in chemical systems. We want to measure precisely the level of weak associative condition, okay? And to do this, we have to develop a method of construction polyquasi group, polyloop, and then apply weak associative laws in investigating precise measure of non-associativity of weak hyper-algebraic chemical systems. We have a method there in which, given a groupoid or a quasi group or a polyloop, you can construct a polygroupoid, a polyquasi group, and a polyloop. So that is what that theorem established, and the examples are given here. I won't be able to speak much to this because I want to concentrate on the analysis of the structures earlier mentioned. Okay, so these are the polyloop that were gotten based on the so we were able to establish that so we introduce some definitions in order to be able to measure the level of weakness, of weak associativity of these chemical structures. So adopting the above definitions and using some properties, some weak associative properties like left alternative property, right alternative property, flexibility, and defining their probability forms, we're able to show, as you can see in this table, this is the algebraic analysis of dismutation reaction. That is, for instance, the left nuclear elements, okay? For the number of those that are true for indium is 8, false 1, for indium plus 7, false 2, for indium 3 plus, those that are true were 8 triples, and those that are false were 1. If you look all through, if you look at flexibility, you will see that for flexibility, they were all true, 3, 3, 3, false 0. So we discovered that that particular algebraic structure was actually found to be flexible. If you look at the second one for the probability, of course, in the case of the probability for flexibility is all 1 or true, while others had 1 in some cases. For vanadium, if you compare the above table, for flexibility, you see that you have one or two again. So which means the hyper-algebraic structure represented by dismutation reaction for vanadium is actually flexible, though not left nuclear, not middle nuclear, and not right nuclear, not left alternative, nor right alternative. 14, the dismutation reaction 14, you have, if you look at it for flexibility, the probability you have one or two as well. And okay, and for the, if you now consider the algebraic structure as a whole, okay, comparatively, you see that for flexibility, they all have a probability of 1 or 2. So when they were not found to be nuclear, though there existed some measure of nuclearity on the left, right, or middle. But for flexibility, the probability was 1. And for left alternativity, the left alternative property and the right alternative property did not hold. So the conclusion is that in this work, we discovered hyper-algebraic structures representing dismutation reactions for indium, vanadium, and tin. They were found to be non-associative. Okay, even though in dismutation reaction for indium, 2 of the elements exhibited high level of being nuclear in the right, left, and middle based on their probabilities in this aspect. Also, it can be concluded that structures formed dismutation reaction has flexibility property. These results were published in this particular paper. Thank you so much. Thank you.
Thank you so much for your nice presentation, Dr. Temitope. Now, any questions or comments?
Can I ask you slides, Temitope? I have sent
Yes,
you
email,
yes. And I can send you interesting paper about hyperring, and maybe you can see some structures and some advices to use hypergroup in the semi-ring. It forms a semi-ring on the base of
hear you very well.
hypergroup.
Okay.
Do you see my email? Yeah.
We have algebraic structures. We have hyper-algebraic structures that are ring-based actually. Hyper rings, hyper field.
Hypergroup ring. Can it be a semi-ring?
Your line is breaking. I can't hear you too well. Your line is breaking. Sorry, I couldn't hear you too well.
I understand.
Okay, all right. Thank you.
Okay. I have a question, Dr. Temitope, about the reproduction axiom. Is commutative?
Okay.
Yes.
Reproduction axiom, yes, of course.
Yes.
It shows commutativity,
yes.
and in particular, the importance of the proportional axiom is the fact that if you use any elements in the hyper-algebraic structure to compose the whole of the hyper-algebraic structure, you get the entirety of the hyper-algebraic structure. That is the importance. And that property actually leads to existence of solution. That is, for 3 elements A, B, C, you pick from H, you are sure that for every C in H, there exists a B in H such that A multiplied by B equals to C. And also for every C you pick in H, there exists a B such that whenever you use A, there exists an A, so that whenever you use A to multiply B, you get C.
Okay, thank you so much for your